Okay, so what did we talk about Tuesday?
Ohm's law.
Yes, the most important thing in this class. Well, Ohm's law is like the most foundational concept we have in electronics and electricity. All right, the other thing we have, so I started you in the lab, I gave you a resistor, you can measure the voltage, you measure the current. By measuring both of those, you're going to prove Ohm's law to yourself by creating a beautiful graph when you're all done. So you'll also be your first attempt, at least for me, to create a graph. We will be creating lots of graphs. You know, like I said, the old saying, picture's worth 1,000 words, that's what a graph is. It's a picture so you can see things more readily. I will tell you, it's a big portion of the grade on that. I mention that because for some reason I have some students that are so terrified of graphing, or whatever it is, that those take the data and turn it without the graph, think, well, they'll take it. I'll tell you, if you do all the work and turn it without the graph, I'll give you like 5 out of 20. Figure it out. And when we get further on, generally my graphs are about half the point. And part of it's because I can look at it immediately and tell if you did it right and if you understand it. That doesn't mean the graph has to be properly labeled, properly have a title that's meaningful, build it the way I told you to in class. If you need help, ask me. I'm happy to help. Every computer in this room has Excel on it, the actual on the computer Excel, which is a little more usable than the 365 version, but they'll both do it. And 365 is available to every student enrolled in college. So I don't care if you use Google Docs. It works fine. I can create graphs in it. I don't care. I don't even know what Macintosh's base system is anymore, but I don't care. You can use any of those you want to create your graphs. I will support Excel because that's what's in. Now, if you get through that first part of the lab, I tell you, get your second resistor, which I will give you. You now have 2 resistors. Those are yours to keep. You will have them available to you anytime you need them in lab because I will give you a little yellow container when you work on the labs afterwards today. We'll put your name on it. You're responsible for all your parts all semester. Don't take your parts home and forget about them and ask me for more. Leave your parts in here to work with. If you decide to, if you have something at home and you're going to take home stuff and work with it, that's great. Bring it back. Most people don't, so I don't know why you take them. Those little yellow containers will go over on the side. I'll put yours on the left side on the top 2 shelves. Everybody in the first semester course will be over on those. I'll move the second semester over to the right. That way all your parts for everything all semester go in there. And you're just available. You pull yours out. Like I said, I'll come around. I got a label and I'll put your name on. Each one of them will contain a little clear container inside full of a bunch of little short wires you're welcome to just use. You always have access to the wire. You can see all the wires sitting on top of the one container in front of the window. You always have access to the wire. You just go grab those spools, use the wire cutters and strippers to make whatever wire you need. But I'll have a little container in there. And there's a little empty container in there which you can put resistors and other parts so you can have it organized. We'll have a couple kits we'll do during the semester. You can build them and leave the parts in there. You can build them and take them home and show them off to mom and dad. I don't care. Once we're done, you got your grade. We'll build a cable. I'd encourage you to take it home, but every semester 2 or 3 people leave them in there when they're done with the class, and I toss them. So whatever you want. You paid for the part, so it's up to you what you do. All right. How many people have done the first part of the lab and got all the data for the graph? A few of you. I'm not really picking on you, but you know the next part tells you to go look at series and parallel circuits. So we need to talk about what series and parallel circuits mean. We already looked at them in lab 1. I had you, or no, lab 2, so this last week. I had you build light bulbs in series and light bulbs in parallel. We talked about how the lighting in an actual house will all be in parallel. That way they all have 120 volts. If we put them in series, they would each have some fraction of the voltage and they'd be less bright. Plus if one burns out, it'll kill all of them. It's going to be an open circuit. So let's talk about this with resistors. So if I build a series circuit, what that means is I have a battery, and then I go through a resistor, and then I go through another resistor. Now for right now, all we have are batteries and resistors and wires. We can have any kind of series circuit we want. The important part about series is that if I leave, I go into something, I leave it, I go into something, I'm going directly. So if you look here, there's going to be a current, charges flow out of the battery. They only have one place to go, and that's into resistor 1. And they're going to flow out of resistor 1, they only have one place to go, and that's in resistor 2. And they're going to come back around and feed into the battery. So everything in series has the same current. There's only one current. Now I'm going to give you a simplified version of voltage, which we'll expand later, which is that series resistor voltages sum to the battery voltage. Again, I asked you this question on last week's lab and said, what do you see when you put these 3 light bulbs in series? You put those 3 light bulbs and you built this thing. So I'm going to pretend this is your 3 batteries in a row, 6 volts. You went out through a light bulb, through a light bulb, through a light bulb. When you measured it, you should have gotten exactly the same current through each one. If I remember right, it's about 80 milliamps, but I don't remember if that's true or not. So that's familiar. So it depends on your specific light bulbs and battery and all. But they all should have been about the same. They're all about 80 milliamps. And each of these was probably about 2 volts. Your light bulbs vary a bit. Sometimes you get one that's way down close to about 1 up by 3. Most of they should all have added up to 6 volts. You should have seen that. If you did lab 2 correctly for the series circuit, that's what you saw. When I looked at the table, I look and go, all the currents ought to be the same. They all ought to be labeled milliamps. They don't have numbers. I don't care what your if they don't have milliamps, I don't care what your numbers are. And the 3 voltages on the bulb should add to the voltage of the battery. So, in theory, identical values. When you measure it in the lab, you might have something out in the end, which is a little bit of change. Okay, parallel. Well, let's do this because we've done power. The power dissipated by the resistors is equal to the power provided by the battery. Now we will expand these some more as we go on. But this part right here is going to be true for every circuit everywhere. The power into the circuit is exactly all the power we take out. That's a conservation of energy problem, concept. Everything I put in, I have to take out. Everything I took out, I had to take in. So if I do calculations for power, voltage times current for the battery, that should equal the voltage times current for resistor 1 plus voltage times current for resistor 2. Or you could have used the current squared times the resistance, or the voltage squared, or all those various permutations we worked through on Tuesday. You can use any of them. If you calculate the power, all the power in ought to equal the power out. Okay, really quickly, conservation of energy, more of a physics science concept, I do realize, but it applies here because it's an applied science. It's a tech area. When I say the term dissipated, that does not mean this energy goes away. What do you think happens to all the energy in there?
Heats up.
Yeah, it turns into heat. Everything we have in here, the amount of heat is so small you won't even notice it. And it's a general rule in here. This is what I suggest, by the way, when I build circuits, I just touch them with my fingers. If they get hot, if they're unhappy, if I can feel it, it's unhappy. Disconnect and get help. Now, when I got higher currents, things get hot enough that they're perfectly safe to use, but I still don't want to touch them. I mean, I'll give you a simple example. The burner on an electric stovetop. What is that? It's just a big resistor that you run a whole bunch of current through and produces heat that you cook with. You don't want to touch it, okay? But it gets hot. That's all it's doing. If you have an electric furnace, it goes through a heating element, which is just a big resistor, and it turns heat. You can blow air across that heat. It blows throughout the house and heats the house up. You know, they're very simple. All you're doing is putting a bunch of current through something, generating a bunch of heat.
Is that safe? Like depending on what materials you use?
I mean, how many people have electric stovetops in their house?
I got one in the dorm. So
Yep.
there.
Perfectly safe.
Yeah.
You know, lots of houses here will have electric heat in the house. They use the same concept. Like I say, you just put a blower so you blow the heat out, and then you push it through a bunch of vents so you can have the heat in the house. Same thing if you have an electric hot water heater. Just produces a bunch of heat. Same concept if you run a blower. Have a little heating element, you just blow a fan across it, blow the hot air out. So they're all just examples of you use dissipated heat to do something you want to do. Other cases, the dissipated heat is a side product that we didn't really want, but it's just there. I know we got a lot of audio students. You don't want to touch the transistors inside a power amplifier. We don't want heat, but it's just a byproduct. They're hot, you can touch them, they'll burn you when they're right at full power. Okay, but everything in here they're going to do in lab, unless I tell you otherwise, touch it. If it gets hot, it's wired wrong. Turn it off and get help. Please do not come tell me it's hot and leave it hot. If you smell things hot like they're cooking, it's probably not happy. Okay, total power. Over here, we dissipate energy as heat, because light bulbs get hot, and light. You can convert energy into different types of energy. You can't make it go away. And you can't have more of that. You can have more out than you put in. If you do calculations in the end, you say, hey, I put 100 watts in and I got 200 watts out. Man, I don't have to do too much to it. No, you can't do that. If you do that, go patent it. Make millions of dollars, but all right, parallel circuits. Again, you did this last week. Parallel circuit. I'm gonna take my battery. So in the lab, you built one where you took these light bulbs and you connected them all in parallel. This is the one where most people had trouble, where I would say not most people had trouble, caused the most trouble for most people. Measuring everything. So if you hooked them up, every one of these got 6 volts. You probably saw when you actually hooked them up that it pulled down the battery to about 5.5 volts, about 5.5, but they're all the same. So, same voltage. Remember my picture of this is the ground, and I go up to a higher level, that's my voltage. These are all the same level, it's just like I have parallel stairs to come back down, or parallel paths to get back down. Here I have one path where I have to go down one and go down the other end and back. Parallel resistor currents sum to the battery current. In other words, I'm going to have a current that's going to be produced and go out of the battery. I'll call it I sub BAT for battery. I'm going to reach this spot, and I have 2 paths. So we're going to have a queued line of things going through, and half are going to go one direction, half are going to go the other direction. It's not going to really be half and half. It's going to be proportional to the resistance, Ohm's law, but it's going to split. So some of the current will flow through this resistor, which is I1. Some of the current will flow through this resistor, which is I2. So I1 plus I2 equals the battery. Because all the current in here Has to go out of it somewhere. Just some goes here and some goes there. It's like you had a big pipe of water. You have splits into two smaller pipes. Some goes down one side, some goes down the other. The specific amount depends on the resistance, the voltage, Ohm's law. Okay, power. This is no different. Power dissipated by the resistors is equal to power provided by the battery. That's exactly the same as here, because that's that whole conservation of energy thing. I put all this energy into the circuit, all the energy I take out, I'll be the same. Producing heat here. Now, when you built this circuit last week, you had 6 volts total. Each of these should have been 6 volts. Like I said, nominally, they probably pulled down the battery to about 5.5 because the battery can't actually provide the current. And if you measured the currents, these currents individually were about 120 milliamps each. You might have gotten 100 if the batteries pulled down enough. If you got vastly different ones, you measured it wrong, and I noted it. And that's the most common error on that one, by the way. So if you measured it wrong, that's fine. That's the toughest thing to measure. You have to make sure you're measuring the current only through that one. A lot of you would disconnect here, measure it, and call it that battery current. Because when you hook it back up, it provides both those. So if you got like a 240 somewhere, that means you probably disconnected it. So you disconnected 2, and we're actually measuring the current both through both. I have to make sure I let this one flow on through to there and disconnect. So it's just this one. I showed a fair number of you of that. If I didn't show it to you, you had to kind of make sure only the one's disconnected. So only one's out. Everything else is working. Then you put your ammeter on and turn that one on. And you would have had about 420 milliamps out of here, which is why this pulled down, because these things can't provide that kind of current very well. What you're supposed to see. It's in theory, that's all. I get those 6 volts and all those currents, but of course, it's a real battery. You can only provide as much current as this little chemical reaction inside can do. Okay. Series, parallel. You're going to build those this week. So the first half of the lab, well, actually, I think the very first part, don't I have you do a bulb and measure voltage and current, calculate power, or calculate resistance? Or do I just go straight to the resistor? I really did a lab last fall, so I don't remember which one it is. But yeah.
Straight to the resistor.
Just went straight to the resistor. Okay, so you hook the resistor up, you measure voltage and current, and you start putting them in a table, and you can plot them.
Yeah.
And I have some things on there. I'll have measured voltage, measured current. You should measure your resistance with the ohm meter, just completely out of the circuit, measure it. Don't measure it when it's connected to power, because it won't work. That'll hurt stuff, potentially. Probably just won't work right though. And then I'll say calculate current. Calculated current. Take your measured voltage, divide it by your measured resistance, and calculate it using Ohm's law. It should look almost the same as the measured. It should be a tiny little difference. Probably because there just will be. Because once you use Ohm's law so many times, it bakes into your brain. You know, your brain should go breathing, Ohm's law. After that, I say, get another resistor. So your first resistor I gave you was a 1 kilo ohm. The second resistor I gave you is a 1.5 kilo ohm. And you're going to hook them up. You got the power supply. You set these up as independent. I believe the lab does have a typo that says set them up parallel. Don't do that. Just set them up independent. And the red, you can connect your little red wire and come out. Black wire. I should probably use red wire. I think that's right. Reminder, you've got to turn the little current knob up a little bit so it can provide current and then turn voltage up. But I'd connect that first. Do not let those 2 ends touch. Somebody yesterday was not getting their voltage up because they had the 2 ends touching. They'd see it. It was just laying over the side. Short circuit. It has short circuit protection, but still. Hook it up first, then turn your voltage up. That way, your make sure you separate those two bits. Don't connect power through my ammeter directly to the ground to measure the current. You have to have the resistor in there. So if I want to come down and do a single resistor, the first part, I just put that resistor in here initially and connect it. So I have a circuit. It's my brown, black, red resistor, 1 kilo ohm. I passed out the other day to everybody. How do I do it? Well, I take a wire and a wire and go over to the voltmeter, which are one I'm picking to use as my voltmeter. I can measure the voltage then, and I can set it to 2 volts or whatever. And I want to measure current, so what am I going to do? I'm going to disconnect those on one end or the other, it doesn't matter which end. I have those connected together, probably some alligator clips or something. And then I'm going to take my ammeter over here, set it up to measure current. Typically I use the one on top for current and the one on bottom for voltage, only because the one on bottom for voltage doesn't use the little double clip, can't go in, double plug can't go in there. And I'll bring its ground over here. It's not touching the red. Okay, it just crosses over it. That way, current, so let me just straighten this out so you can see one more. Current flows out through the ammeter, through the resistor, into the circuit, and I'm measuring the voltage across it at the same time. If I want to, I can actually hook the voltage all the way over here. That might be better. If I wanted to draw this as a diagram, I will show it as the voltage source. I will go through the ammeter to the resistor and out, and over here I will connect the voltmeter. So the voltmeter is connected around the resistor. I flow through. My resistor has to be in there. Maybe just start checking things. Hopefully everybody started this on Tuesday, but there's some little red and black wires that plug into this, and they're alligator clips you can slip on the end to clip onto your resistor. Okay, that's the first one. In theory, probably should have been done before today. Because today you want to be working on the next stage, which is the series and parallel. So if I want to put 2 resistors in series, I'll add that ammeter all later. I got to run out of one resistor and into the next. So if I'm going to come over here, take my little measuring devices out. I'll probably need now. Need to go get an alligator clip or something out of the bag to connect those 2 together. Now I go through 2 resistors in series, out of one and into the next. And now I'll just flip them up with little alligator clips. Those of you who know how to use a breadboard, I don't care if you use the breadboard, but you cannot connect the power from the separate power supply to the power supply built in the little trainer unit. You can just use the little dumb breadboard part. If you don't know what I'm talking about there, do not do it. Just lay it on the table and work with it. I'll teach you how to use breadboards in a couple weeks. That's the series circuit. I can come in then, measure voltage across each resistor. I can break this circuit anywhere and measure the current. I have a series circuit. If I measure the current here or here or here, they'll all be the same because circuits in series have the same current. These 2 voltages will be different from each other because you have 2 different resistors, but they should add up to the voltage from your supply. Then I'm going to take this. I may tell you parallel first. I don't care which order you do it in. As long as you know. If you can do one, then do the other. If I'm going to do parallel, I just hook one resistor up here and the other up here in parallel. Then I should be able to measure the same voltage across each. To get current, if I want to get current, I would disconnect just one resistor and leave the other one still connected. And then I would run these off to my ammeter. So just, hey, looks just like, so it's just measuring the current for that single resistor. So anytime you want to measure current, you only break the thing you want to measure through. I noticed a lot of this last week, a lot of people, and it's, by the way, it's happened every semester, so it's common. Current measuring is tough. it's, I don't, I think physically, I think getting the idea I have to put the thing in makes sense, but how do I actually physically remove it? It's just, you have to do it so everything else is still connected except for that one element you want to measure. And you put it back in. A couple other things. A big thing, and I stress this in the homework. Do not, under any circumstances, connect the positive battery to the negative. Or connect the positive of my power supply to the negative, because you're asking for infinite current, which is going to blow the fuse in my ammeter if we're lucky. I have a couple ammeters that are burned out because people did that and just fried them. Don't do that. There's nothing good, because Ohm's law. If you do that, you're saying, hey, take my voltage, divide by the zero resistance in my ammeter. So please give me an infinite amount of current. I really like infinite current. We can't do that. This can give you enough to blow the fuse. In fact, some of these in here we can actually get enough to maybe hurt you, which can't hurt you otherwise, but that might. Probably not. Don't do it. All right, other questions? I moved fast today because we covered most of everything Tuesday. I love to give you lots of class time to work. Yeah.
I'm just kind of struggling to understand this picture for parallel. Is that coming off of?
How about we set up a lab over here and I'll show you something by a picture on the board.
Okay.
So let me start recording. Look at that. I only have one